Gravitational potential energy 3. Here we will show that when objects are near a planet's surface and undergo elevation changes that are a small fraction of the planet's radius, the easy gravitational potential energy equation from first-year physics, delta U is equal to mgh, is valid. At right, the mass m is near the surface of a planet of mass big M and radius big R. Little m starts on the surface and is then elevated to a height h above the surface. So that is what's happening here. And we're going to hopefully prove to you that if you're close to the surface of a planet, that the equation for calculating change in gravitational potential energy is that real easy one, m times g times delta h. So let's try this. Using absolute gravitational potential energy, write equations for when the mass is on the surface and at elevation h. Absolute gravitational potential energy is equal to the opposite of g, one of the masses, the other mass, divided by the distance between them. So that's when we're on the surface. When we raise this thing above the surface, the numerator is going to be the same, but now the distance between them is r plus h. We now want the difference in gravitational potential energy. The difference in gravitational potential energy is final minus initial. Final is this one here, negative g big M little m divided by r plus h. Final minus initial, right? Minus the opposite of big G, big M, little m, divided by capital R. All right, so what can we do here? Why don't we get a common denominator? That means that I'm going to multiply this thing here, aren't I, by R over R. And then this thing here, won't I multiply by the quantity R plus H over R plus H? Let's see what that gives us. We multiply that out, we're going to get negative big G, big M, little m, big R over R plus H quantity multiplied by R. That's the denominator. Minus, and then here we're going to put that negative G, M, M, put that in parentheses, times the quantity R plus H, and then in the denominator, same thing. R plus H for R, kind of like that. Now, what does that give us? Obviously, the denominators, we can combine those, so it's looking like we need to simplify the numerator. And in the numerator, I'm seeing here negative big G, big M, little m, R. And if we do the distributive property with this, you see that I'm getting, there are a couple of negative signs, so that's a positive big G, big M, little m, R. So the only thing that doesn't cancel in the numerator is when we take that. Stop the video if you need to and check to make sure I've done that right, but I think we're good there. Big G, big M, little m, H, and then in the denominator, we've got, I'll go ahead and distribute that as well. How about that? R squared plus R times H. What does that mean for us? That's our change in gravitational potential energy when we used absolute gravitational potential energies. What assumption can we use to simplify this answer and then apply that assumption? The assumption is, if we're close to the Earth, H is much, much, much tinier than big R. And if H is much, much, much tinier than big R, we can't do anything with the numerator because little h is multiplied by everything. But in the denominator, if h is really, really tiny, that means that this r squared term is really the only one that's relevant. So then what we simplify this to be is G, M, little m, H over r squared. And in an earlier video, we showed that big G times big M divided by R squared, that's little g. And what does that give us? Look at that, mgh, exclamation point. Pretty neat. So if we're close to the surface of a planet, we can find gravitational potential energies using mgh, or mg delta h if you want to change the elevation and find the change in potential energy. If we're talking about the whole planet, if the picture shows the whole planet, you cannot use this simplified version. You have to use the more complicated absolute gravitational potential energy, from which we derive that simplification.